Okay, everyone. So we're going to get underway. I actually accidentally forgot to record the beginning, and so I'm actually recording this after the fact, but we'll try to edit it into the beginning. And so we're going to go up to partial pressures, which is when I actually remembered to start recording during the actual session that was taught tonight, November 11th. So tonight's session actually doesn't begin with challenge problems because on Monday we only went over chapter 7 and we didn't get quite as far as I thought we might, which is completely okay. But half of the challenge problems anyways regarded material we didn't even get to. So any of the problems from Monday's session that we did cover the material for, we'll review those challenge problems the next SI session, and anything having to do with quantum numbers, those problems will be added to Monday, the 16th's challenge problems, and we'll review them the following session, right? So we'll go over quantum numbers next SI session on Monday, and then go over the challenge problems regarding that material the following session. Okay, tonight's challenge problems, remember, this is the last session before an exam, and so an additional video will be posted where I go through it's 7 challenge problems regarding chapter 5 and 6. Okay, and so one thing I wanted to bring was just one practice example for us to look through, something I found in my notes from, I believe, a student from office hours last year that had brought me this problem. And basically it's a calorimeter problem, but you're dealing just with water, and it's a little bit different than we're typically used to. So I just kind of wanted to go over this in the reasoning behind it, right? So you have 100 milliliters of 92 degrees water that's added to a bomb calorimeter that already contains 115 milliliters of water at 20 degrees Celsius. You're then told that the water equilibrates at 52 degrees Celsius, right? So the final temperature for both of these samples of water will be 52. And it says, what's the heat capacitor of the calorimeter in joules per, joules per degree Celsius, and you're given the specific heat of water. Okay, so we're being asked for the heat capacity of the calorimeter, which means one of these samples of water, the hot or cold water, needs to use the Q, or heat equation, that involves the bomb calorimeter. Okay, and we're going to use that for our cold water, the one at 20 degrees Celsius, because that's the one that was in the bomb calorimeter at the start of this reaction, right? So we have 2 different portions of this problem, the Q lost, or the heat lost, and the Q, or heat gained, right? And so the hot water is going to become colder, therefore the hot water is going to be Q lost, and the colder water that gains heat is going to be Q gained. Okay, so we have 100 milliliters, or 100 grams of that hot water, right? Because the density is 1 gram per milliliter. The specific heat capacity of that water is 4.184, and we do the change in temperature, which is final temperature, 52 degrees Celsius, minus initial, 92 degrees Celsius. This gives us, this tells us that 16,736 joules of energy was lost from the hot water. And where did they go to? They went to the cold water, Q gained, which would be positive 16,736 joules. See, equal in magnitude, but opposite in direction, meaning opposite in sign. Okay, and this Q would be equal to the mass of our cold water, 115 grams, times the specific heat of that cold water, times the change in temperature, which would be the final temperature, 52, minus the initial temperature, 20. And to this, we have to add C bomb times delta T, right? This portion, this term, is because this is occurring in a bomb calorimeter. And when we solve for our heat capacity of our bomb calorimeter, it comes out to 41.8 joules per degree Celsius. Okay, so really this was to show that this calorimeter equation should be used with Q gained, because this represents the cold water that was in the bomb calorimeter, right? When this reaction started, the cold water was already in our calorimeter, while the hot water was being added to the calorimeter. Okay, so here are our topics for chapter 5. Okay, so we're going to kind of go through these. I'd say the big note is on density. I actually kind of overlooked something when we originally taught it, and I do apologize for it. And so we will kind of go over that a little bit more in depth. okay? So just a quick reminder of barometers and manometers, right? So remember the barometers, which were shown here, right? This is our barometer, measures atmospheric pressure, right? And so a barometer has kind of like a cylinder portion, and then it has a tube coming through the middle, okay? And this is filled with mercury. And what happens is atmospheric pressure comes down and pushes the mercury down and into and up this column, okay? And so there's going to be a height differential between the height of mercury level in the column and our cylinder section, okay? And that height differential will be measured in millimeters or centimeters of mercury, right? So millimeters mercury or centimeters mercury, which we could convert to torr, okay? But the barometer, which measures the atmospheric pressure, will give us a reading where that our atmospheric pressure is equal to that height differential, okay? So besides barometers, we also have manometers, which measure the pressure of a gas within the device, right? So it kind of has a curved shape, and it has this kind of circular chamber where gas resides, okay? And we're measuring the pressure of the gas in that chamber. So we have two different types of manometers. We have closed and open-ended, okay? And so these two top diagrams represent closed-ended manometers, because as you can see, the end on the opposite side of the gas, right? So the gas is in this kind of circular part. This other side could be open or closed to the environment. And this is closed, as we can see. And so in a closed-ended manometer, you can never have a situation like this on the left, where the level of mercury is higher on the side with our gas on it. The reason for it is on the other side, the closed side, we have what we call a vacuum, which cannot exert pressure. Therefore, the height differential of the mercury will be level, or it'll look like this on the right, okay? So the height can be of the mercury can be higher on the closed-ended side, but it cannot be lower on that closed-ended side. That's not possible, okay? And so if we have a manometer that's closed-ended and we have a height differential like here, the pressure of our gas would just be equal to that height differential, right? So again, if the height is 400 millimeters, or the pressure of our gas would be 400 millimeters mercury, okay? Now we also have another type of manometer called open-ended manometers. So as you can see, when we look across from where our gas is, this side is open, so it's exposed to the environment, and the atmospheric pressure can come down and push the mercury down, okay? And so in a circumstance where the level of mercury is level, right, so there's no height differential, this means that the pressure of our gas in the manometer is equal to the pressure of the atmosphere, okay? And from kind of this medium position, we have two different circumstances we can see in which we have height differentials. Okay, and so if we have a height differential and the level of mercury is lower on the side exposed to the atmosphere, that means the pressure of the atmosphere is greater than the pressure of our gas by a quantity equal to H, okay? And so when we're solving for the pressure of our gas, that means the pressure of our gas is equal to the pressure of the atmosphere minus that height differential, okay? So again, the pressure of our gas is going to be less than the atmospheric pressure by an amount equal to that height differential, okay? The other circumstance we can see with an open-ended manometer where we have a difference in height is where the level of mercury is lower on the side with our gas. And what that means is that the pressure of our gas is greater than the atmospheric pressure by an amount equal to the height difference. Okay, so P gas equals the atmospheric pressure plus H for that circumstance. Okay, our ideal gas law, so I'm assuming by now that you're very familiar with PV equals nRT. Pressure is measured in atmospheres, volume is measured in liters, N stands for moles, temperature is measured in Kelvin. Remember, our ideal gas law constant is 0.08206. And it is that R value versus the other ones, okay? So definitely make sure maybe on your equation sheet that you discern between the different R constants and when you should use each of them. Okay, and kind of some theoretical notes about the ideal gas law. Remember that when we use it, we're assuming that gas particles occupy no space, right? Which means that the assumed or ideal volume that we use is greater than the real volume, okay? The other assumption we make is that gas particles do not interact and collide with one another, okay? And so this assumption, this assumed pressure, this ideal pressure is going to be lower than the real pressure that should have been recorded or calculated, okay? Moving on to change problems. So these are problems in which some conditions in the ideal gas law change, and you're asked how one variable changes in response. So for example, maybe pressure and volume will change, and they'll say, based on these changes in pressure and volume, what is the effect on temperature? Okay, and so you'll be asked to find maybe a final temperature. Okay, and so below I show you the general setup, right? P1 V1 over N1 T1 equals P2 V2 over N2 T2 is your general setup that you're going to use for any change problems. Okay, but any variable that does not change during the problem or a variable that they do not mention at all, you should take out of the expression, right? It's just going to complicate things. And so for example, if in a problem they tell you the number of moles does not change, right, you would cancel out N1 and N2, and you'd be left with the simplified expression P1 V1 over T1 equals P2 V2 over T2. Okay. Moving on to density. So as you can see, this is the derivation of density. So density would equal to our pressure times our molar mass over R times T. But if you actually look at the units of this, you would find that the density in this equation has to be in terms of grams per liters. Okay, this is something I had previously overlooked. And so when you plug in density into this equation, you have to convert the density given into grams per liters. Or if you're solving for density, realize that whatever numerical value you get from this calculation will be in terms of grams per liters. Okay, so that's very important. I am unsure of an example in the live, like Dr. Homan's lectures, where he went over an example of this, but I know from previous years, if you go into the folder, I think it's 10-09, like week due 10-09, so October 9th. If you go into Dr. Katie's old files, he goes over an inflatable tube example that's good with density. And so if you feel uncertain about it, or even if you don't, I do recommend looking at least at that example, because it is really important to note that this density is in grams per liters, not grams per milliliters. And the reason why is the liters is in our ideal gas law constant R, right? And so when you cancel out these units, it's grams per liters. Okay. Gas over water questions. And so the typical setup for this is you're going to have a test tube with typically a solid in it, right? It's going to be heated by a flame. And one of the products, right? Typically there's more than one product, but the product is almost always oxygen gas, okay? It could maybe be a different type of gas, but the most classic example is it produces oxygen gas. Okay, then this oxygen gas is going to go through a tube into some water and then travel through the water to become, to kind of reach open air, right? But what we have to realize is that above every container of water is going to be some amount of vapor, like water vapor, right? And so that water vapor is going to be a contaminant to the oxygen gas we're trying to measure the pressure of, okay? And so kind of a key phrase to a problem like this is you will almost always see the phrase collected by the displacement of water, right? And so even if it's a different gas, if they say this gas is collected by the displacement of water, you know it's a gas over water problem. And in your typical problem, you're given your total pressure, your vapor pressure of water at a specific temperature, a temperature, and the volume. Okay, and they'll typically ask you for grams or moles of starting reactant you had. So how you approach this problem is you have to realize your total pressure is equal to your vapor pressure of water plus the pressure of your oxygen gas, right? Through that, you can solve for the pressure of your oxygen gas. Once you have pressure of the oxygen gas, you can convert using your ideal gas law to moles of oxygen gas, and then you can use a balanced chemical equation to stoichiometrically convert to starting reactant. Right, that's your typical problem. Okay, stoichiometry. So remember, stoichiometry really just means interconverting between compounds in a balanced chemical equation. Okay, and we do this through moles, right? When we convert from reactant to product or vice versa, we're going to use moles and our coefficients in the balanced chemical equations to interconvert. Okay, you could see limiting reactant questions and problems in this chapter, right? So remember, if you're giving multiple starting amounts of reactants, check to see which one can form less product. Whichever reactant forms less product is your limiting reactant, okay? And then from there, they could ask you maybe excess. So knowing how to work backwards to find excess moles of the other reactant can also be important. And so stoichiometry in this chapter kind of appears in this format, okay? And so our typical stoichiometric problem before this chapter is we get grams of a reactant. We use the molar mass to convert to moles, right? We use our balanced chemical equation to convert to moles of product, and then maybe report how many grams of product we're able to make. But we're dealing with gases. And so in this chapter, what they'll often do is they'll give you the pressure, volume, and temperature of some compound, right? And using the ideal gas law, you can find moles of that compound. Then you can use your balanced chemical equation to find moles of product. And then for moles of product, they can either ask you for how many grams of product you have, how many moles of product you have, or they can ask you for your pressure, your volume, or your temperature of the product. They cannot ask you for all three, okay? They'd have to give you 2 out of these 3 for you to solve for the one unknown. But that is a way it could appear as well, okay? At this point, we're at partial pressures. This is where the actual live SI picks up. And so this is where I will leave it and let that recording continue from here. Okay, best of luck studying to all. Moving on to partial pressures, right? So partial pressures we use whenever there's more than one gas in a chemical system, okay? And so really the only note I have besides the equations is remember that volume percentage is analogous to mole fraction, right? So if I say that a container is 60% oxygen gas by volume, right? That means its mole fraction, which is always going to be a decimal, would be 0.6, right? 60% volume is equivalent to a mole fraction of 0.6. Okay, so if you ever seen volume percentage, I suggest you kind of change it to mole fraction. And the reason why is you can actually use mole fraction according to this second partial pressure equation, which we'll get to in just a second. Okay, so the first partial pressure equation we have is that the total pressure is equal to all the partial pressures of each of your individual gases, right? So if you have 3 different gases in a system, call them gas A, B, and C, the partial pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C would equal our total pressure. Okay. Now we also have this relationship here that says that the partial pressure of an individual gas is equal to the mole fraction of that gas times the total pressure. Okay, and that's why our volume percentage being analogous to mole fraction is important, because oftentimes they'll give you a bunch of gases and say, here are their volume percentages, and if the total pressure is this, 1 atm, what are all your partial pressures? Okay, and so for there, you'd have to note that your volume percent is analogous to your mole fraction, and then you'd have to plug in your mole fractions in your total pressure to find all of your individual partial pressures. Okay, and just a reminding note that mole fraction you calculate by taking the moles of some species and divide it by the total moles, right? So the mole fraction of oxygen gas would be moles of oxygen divided by total moles in the container. Okay, and then the last kind of partial pressure equation we have is really just our ideal gas law, right? But when we typically use our ideal gas law, we're really saying our pressure total equals our total moles times R times T divided by our total volume. Here we're saying, well, we can also use the ideal gas law for just a single gas, right? So if we have multiple gases in a container, we can say that the pressure of one gas is equal to the number of moles of that gas times RT divided by V, okay? And there's no A subscripts next to temperature or volume, because typically those variables are the same for every gas in the container, right? And so they're constant from one gas to another. So just a couple quick notes about the real gas law, also known as the van der Waal equation. And so could they have you do a numerical, like some kind of plug and chug question with this on the exam? Yes, it is possible. If they give it to you, it would typically be presented in a pretty straightforward way, right? They would probably give you every single variable you need, except for one, right? They might say solve for this, and they should give you every other value that you need to plug into this equation and eventually solve for that one value they asked you for. Okay, so that's my one kind of comment about if you are approached with a problem like this on the exam. I would say plug in all your values. You should have all you need to solve for it. It would just be an algebra question. Okay, but kind of understanding the real gas law or the van der Waal equation, right? So you can see the volume looks a little different. It's not just V, it's V minus NB. And this is our adjusted volume, right? And so we're using real gases, right? We're no longer using those assumptions that we made for the ideal gas law. And so V minus NB has this term negative NB or minus NB, which represents the volume of space the gas molecules occupy, right? So in the ideal gas law, we assume no gas molecules occupy space. But in the real gas law, or when we get rid of that assumption, we're going to say that that space that they do occupy is equal to negative NB. Okay? Pressure, again, we're kind of acknowledging attraction and collisions between gas molecules, right? Which those collisions and those attractions create added pressure, okay? And to quantify that added pressure, it would be A times N squared divided by V squared, okay? So this term here represents the added pressure we have by acknowledging that molecules interact, okay? And so all of this, P plus A times N squared over V squared, represents our adjusted pressure, okay? And A and B are just, they're constants. So they're not constants, but they're, yeah, I think maybe a constant. They might have to do with like temperature or something like that, but they would be given to you. Or again, you'd be asked to solve for it. But if you had to do this on an exam, you'd most likely be given the values of A or B. Okay. Okay, kind of wrapping up with chapter 5. So we have our kinetic molecular theory. So this stuff doesn't really tend to show up much on the long answer, so I'm just going to kind of quickly skim over it. And so one relationship we have is with the average kinetic energy, right? And we could see that that is equal to 3/2 times RT, meaning our kinetic energy and our temperature are directly proportional, right? It's also equal to 1.5 PV over N. I really wouldn't expect to see anything about that on a long answer portion. If you were to see anything on this slide on a long answer exam, I would expect it to be your root mean squared velocity or effusion calculations. Okay, and so root mean squared velocity, it's pretty complicated. It's basically the average velocity of a particle, right? Because at a specific temperature, right? So not all diatomic nitrogen molecules are going to move at the same exact speed at the same temperature. That's just not possible. And so this basically finds what's the most likely velocity, right? What's almost like the most common velocity we see. That's what root mean square velocity is calculating. And it's equal to the square root of 3RT divided by our molar mass. Okay, now the two biggest things to emphasize about this, well, first I'll just mention that temperature has to be in Kelvin. That's very important. But the two more important things to point out, or at least equally important things, is R in this equation is actually not your ideal gas law R. It is actually 8.3145 joules per Kelvin moles, right? And so it's super important. If you're going to write anything on your kind of equation sheet, this is definitely something that I would make note of, okay? Because this is a different R value than we've previously used for all the ideal gas law. Okay, and then the other really important thing is that the molar mass that we input into this equation has to be in terms of kilograms. And the reason for this is joules is actually a bunch of units multiplied and divided together. As a unit, it's pretty complicated, but when you cancel things out, when you do all of this math, your units come out to meters per second for velocity, which makes sense. Okay, so your molar mass has to be in kilograms, and remember to use this different R value if you have to use this equation at any point. Okay, diffusion, again, another thing that I wouldn't expect to be on this exam, but remember, diffusion's just movement of gases, and they're random movements. They become more mixed, right, to kind of reach an equilibrium by being as far apart from each other as possible. They move down kind of a gradient, right? So they don't aggregate, they try to move away from each other. And basically what we've learned about diffusion is that the higher the molecular weight or the molar mass, the slower the rate of diffusion, right? We weren't really given, besides our root mean squared velocity, we're not really given any other way to directly calculate diffusion. And so really the only note other than root mean squared velocity is that the higher the molecular mass, the slower the rate of diffusion. In terms of ability to calculate, though, you can actually calculate effusion, okay? But we actually calculate it as a ratio, not on its own, okay? And so what is effusion? So remember, effusion is the passage of a gas through a tiny hole into an evacuation chamber, which is like a different compartment. Basically, effusion is similar to a diffusion. It just almost has a purpose, right? It's how long it takes for, or what's the rate of molecules going through this one specific point. And so again, we calculate this as a ratio in, I believe it's called Graham's law of effusion. Okay, and so it's the rate of fusion A divided by rate of fusion B equals the square root of the molar mass of B divided by the square root molar mass of A. Okay, in this equation, you can use grams or kilograms for your molar mass. You just need to stay consistent between B and A. And I would just note that it's your molar mass of A that goes in the denominator, even though the rate of gas A is kind of like in the numerator. Okay, and this will get you some decimal that may or may not have an integer in front of it. Okay, and so you might do this math and get 1.36, and that means that gas A would move 1.36 as times as fast as gas B, right? So 1.36 means gas A moves 1.36 times faster than gas B, okay? Okay, let's just kind of take a break for a second there. Please use the chat to sign in using your net ID, and just kind of think about if you have any questions relating to any of the chapter 5 topics up to this point. Okay. Okay. Now, are there any questions? I know people are still kind of signing in, but are there any questions relating to chapter 5? Which is our gas laws.
I know it was like a while ago, but do you remember which week you went over chapter 5, just so I can go over some practice problems from it?
It would have been 2 weeks ago and 3 weeks ago, if that helps. So I can't mentally think of what weeks that are. off the top of my head. But yeah, so we spend about 2 weeks going over each chapter in SI, right? We kind of take the first week to actually go through that chapter. Then the second week, we kind of do some review and maybe move on a little bit. And then the fourth session in that 2-week block is going to be a review of the chapter and the chapter before it. And so, yeah, if that kind of gives you a guide, I would say the Monday session 2 weeks ago, so now 16 days ago, whatever session that was, that session, I believe, went over a couple different types of problems relating to gas laws, but much slower. So I think we went over a limiting reactant problem in gas laws. And then I think we went over 2 different types of collecting gas over water questions. I think it was that session that we kind of walked through less types of problems, but more slowly and more kind of methodically. If that's kind of the thing you're looking for, if not, the week before should be kind of more of the general going over the entire chapter. Okay, so we're going to jump into chapter 6. So we're going to start just by going over some basic definitions before kind of just hitting on heat exchange, our calorimeters, and then finishing up with enthalpy. Okay, so again, I'm sure you're pretty used to heat capacity by now. And specific heat capacity, it's the energy required to heat up something by 1 degree Celsius. The only difference about specific heat capacity is it's how much energy is required to heat up 1 gram of that substance by 1 degree Celsius. Okay, and so specific heat capacity we'll typically see for like water and metals and things that we want to use Q equals MC delta T for. Really, for the most part, the only time you'll see heat capacity is with bomb calorimeters, right? Because remember, in that equation, we're going to have Q of water equals MC delta T plus the heat capacity of our calorimeter times delta T. But we'll see that equation, I believe, on the next slide. Okay, remember we have our system and our surroundings, so kind of our 2 components of thermo reactions, and we kind of classify the system as what we focus on and the surroundings as everything else. But in the problems we do, right, your system is typically a chemical equation, right? It's probably some chemical reaction occurring, maybe in a calorimeter, or whenever I do a heat exchange problem, like a hot piece of metal into cold water, I always think of my hot metal as my system. Okay, and then our surroundings, most of the time, is water, right? It's water in the calorimeter. It could also be, yeah, it's almost always water is what we kind of think of as our surroundings. Okay, you would say that surrounding air and anything else that takes away heat from the system is also your surroundings. But again, in this course, we kind of oversimplify what our surroundings are. And so for our calculations, our surroundings will pretty much always just be water. Okay, and then we have 2 terms that are very important. It's endo and exothermic. Okay, an endothermic reaction is when the system gains heat, also known as absorbing heat. And an exothermic reaction is when the system loses or gives off heat. Okay, so endothermic reactions are going to have positive Q and delta H values, while exothermic are going to have negative Q and delta H values. Okay, and so something really important about these 2 terms is that they're in reference to the system. Okay, so if the system loses heat, it's exothermic. If the system gains heat, it's endothermic, right? You won't really see it. There was a problem that we did on Monday where I gave you information. I said that the water, I think, heated up, right? So the water gained thermal energy. And from that, we said that the reaction is exothermic, okay? And it's important that the term exothermic is still referring to the actual chemical reaction itself. We just knew that information about the reaction because of the clue that we were given that the water increased in temperature. Okay, so the term exothermic was still in reference to the actual chemical equation occurring. Okay, heat exchange. So the classic example of this is just, again, kind of like a piece of metal dropped into water. And so we have kind of two main equations that you need to solve these types of problems. The first one is kind of your big heat relationship that you use in most problems. And this is that the heat gained is equal to the negative heat lost. Basically, the energy that you lose and the thermal energy you gain will be equal in magnitude, but opposite in direction. Right, so that's kind of like the key point there. And the general equation that you'll actually plug numbers into is this one, Q equals MC delta T, where Q just means heat, and we typically report it in joules or kilojoules. M stands for mass, and it's in terms of grams. C is for specific heat capacity. It'll be given almost always in joules per gram degrees Celsius. And then our change in temperature, remember delta, or that triangle, always means final minus initial, meaning it's our final temperature minus our initial temperature. Okay. And one other comment about heat exchange, and if you didn't see this problem, it was in last Monday's SI session, so 9 days ago. I believe one of the challenge problems from that night involved, it was heat exchange, just like a classic one, but it was a little bit more complicated by the fact that there were actually two pieces of hot metal added, and they were different types of metal as well. They were made of different elements. That problem is a little bit harder than you'd probably see on an exam. On an exam, it would probably be a classic problem where it's one hot metal and a beaker of water. But they could give you multiple hot or multiple cold metals as well. So if you haven't seen that example from last Monday, definitely check it out. And even if you have seen it, go back, review it, make sure that you're comfortable with the heat exchange problem if there are more metals involved than just one, right? If there's 3 species exchanging heat, can you do those calculations? Okay, and a key to heat exchange problems is knowing that all the species involved should have the same final temperature. Okay. Okay, calorimeters. So we have 2 types of calorimeters. We have coffee cup calorimeters, which is shown over here, and then we have our bomb calorimeters. Okay, and we're going to treat them very similarly. Okay, and so how these reactions, how it's typically set up is we have a chemical reaction occurring within the coffee cup calorimeter, and then we have water in the calorimeters as well. And these, this water is what is our surroundings, right? So the reaction, it would have been last Monday, 9 days ago. Okay, so there's a chemical reaction occurring in the calorimeter, and then based on whether that reaction is endothermic or exothermic, right? It's going to give or take heat from the water, and we can measure that change in heat of the water via a thermometer. Okay, so you'll typically be given some change in temperature of the water. And again, one of the key equations to use in these problems is that the Q of system equals negative Q of surroundings. Again, equal in magnitude, opposite in direction. Your system will more likely than not be, again, a chemical reaction occurring within the calorimeter. Your surroundings, more likely than not, will be your water, right? And so for a coffee cup calorimeter, we use Q equals MC delta T to calculate the heat of our water, okay? In a bomb calorimeter, it's slightly different. So we have a same setup where we basically have a reaction occurring, that is our system, right? And we have our water, our surroundings, in the bomb calorimeter as well. The difference is that the heat of the water has the heat of the water has a slightly different equation. We'd find the heat of the water, or the heat of the surroundings, by doing Q equals the mass of our water times the specific heat capacity of our water times the change in temperature, plus the heat capacity of our bomb calorimeter times the change in temperature. Okay, so this C bomb times delta T portion is the difference between your calculations in a coffee cup and a bomb calorimeter. Okay, and again, it probably won't come up on a long answer exam, but why do we have a bomb calorimeter? Well, we use it when we're doing reactions that require really high temperatures, right? A coffee cup wouldn't be safe for that. And we also do it when it involves gases.
So, quick question on that.
Yep.
So when we solve for these, are we setting like just like the change in the water equal to the negative change of the surroundings then? Or like the Q of the system, are you setting like the two equal to each other and then solving for whatever variable? Oh wait, actually.
So it depends on the information they give you, but yes, you are going to have to use the idea behind Q of system equals negative Q of surroundings, right? And it doesn't really matter which one you put the negative sign in front of. All that relationship is saying is that they're equal in magnitude, opposite in directions, okay? And so your typical problem you'll see tonight in the challenge problems, I give you the heat evolved during a chemical reaction, and you solve for basically your unknown variable.
Okay.
Yeah, they'll give you all the information you need, except for one variable. You just kind of need to be able to use these two relationships in conjunction. Okay. Enthalpy, remember it's the difference in heat content between reactants and products at constant pressure, and it's a state variable, right? Which means we don't care about the path the reaction took. It's just what was our initial and our final conditions, right? Again, how it got there, we don't really care. And again, these notes, a little less important for a long answer exam, but do remember that challenge problem I gave you the other night that was actually kind of like multiple short answer questions. And one of them was true or false, and it had to do with enthalpy being a state variable. Okay, and so that could show up. So definitely look at your theoretical notes, but realize it's a long answer exam. It's going to be more calculation heavy than your multiple choice. In measuring enthalpy, so we have this general equation. We're going to go over that on the next slide as well. So kind of the takeaways for this slide is that if you get a positive delta H for a reaction, that means your reaction is endothermic, right? If you calculate your change in enthalpy for a reaction and it is less than 0, also known as it being negative delta H, that means you have an exothermic reaction. Okay, and so I'm going to actually kind of skip down to the second point before coming back up. So sticking on enthalpy, so a common type of question is they'll ask you what the enthalpy change for a reaction is, and they will give you enthalpies of formations, right? You'll see delta HF in a table. That means the enthalpy of formation. That means that's how much energy it takes to make that chemical compound. Okay, and so given a chemical equation, a balanced chemical equation, you can use a table of values to solve for the delta H of that equation. And how you do that is you're going to add up all the enthalpy of your products, right? So you're going to add the enthalpy of all your products together, and from it, you're going to subtract the enthalpy of all your reactants added together, okay? And so again, remember, these values are going to be given in a table, okay? The values also are dependent on the state of matter, okay? So just because you see water in your equation, be careful, because in the table they might list the value for liquid water. They might also give it to you as solid water, which is ice, or gaseous water. And so make sure that you're using the correct value that corresponds to the correct state of matter, okay? And then if you're ever trying to do one of these problems and you don't think you're given enough information, maybe there's something in the chemical equation that doesn't have a value in the table, realize that anything or any element in its natural state will have an enthalpy of formation equal to 0, right? So if you're not given a value, it's probably because you don't need it, right? So diatomic oxygen, O2 gas, would have an enthalpy of formation equal to 0, right? Iron solid, Fe solid, would have an enthalpy of formation of 0, right? Chlorine gas, Cl2 gas, enthalpy of formation of 0. Okay, so again, if you're looking and there's some compound that you don't have the number 4, it's probably you're either solving for it or it's the natural state of that element and it's 0. Okay, Hess's law problem. So we've gone over quite a few of these in the past, but what is a Hess's law problem if you're unfamiliar with it? It's a type of problem where they give you a goal reaction, right? So, or at least that's what I call it. And they said, find the enthalpy of formation of this goal reaction. And then they'll give you typically 3 reactions below it that I kind of call sub-reactions, okay? And basically all it is, it's a multi-step reaction, right? It's a multi-step reaction. And so you're going to try to add those steps together in a way that gives you what we call the goal reaction, okay? And so you might have to manipulate these sub-reactions along the way to get that goal reaction they want you to find your delta H for. Okay, and the key to these problems is to identify compounds in the goal reaction that is only in one sub-reaction. Okay, and the reason for this is if something appears as a product in the goal reaction, for example, and it is only in one sub-reaction as a reactant, right? By looking at that one chemical species, you can figure out how to correctly manipulate that whole equation. Okay, and so I say identify something that's unique to each sub-reaction, right? Then look and see how it appears in your goal reaction, and then make the necessary manipulations to your sub-reaction, right? So if you have to multiply your equation by a coefficient, remember to multiply your delta H by that same coefficient, right? Because you have to manipulate your delta H as well. And remember, if you ever have to flip an equation, so your reactants become products, your products become reactants, remember you have to change your sign on your delta H, okay? And once you've correctly manipulated all your equations to find your delta H of your goal reaction, you just add up the delta H's, okay? And then I think this is kind of the last topic for this chapter to cover, and it's phase changes. And so something I always do for these problems is I draw a little diagram like I did down here, just to help me visualize this process. But just a couple of notes is that remember that when you're changing phases, your temperature actually stays constant, right? So this horizontal line here is when all my gas molecules are condensing into liquid, right? It's going to stay at 80 degrees Celsius. And then as soon as every single one of those becomes liquid, all those particles, then they'll start cooling down further as liquid. But your actual temperature will remain the same while you're going from gas to liquid during condensation, okay? Other notes is remember that when you're in different phases, remember you have different heat capacities, right? So your specific heat capacity of liquid water is different than ice and steam. So remember to use the correct heat capacities based on where you are during your phase change. And then kind of the last comments are on our actual processes of changing phases, right? So we have endothermic changes and exothermic changes. So going from melting, so going from a solid to a liquid, or like boiling, vaporization, liquid to a gas, those are endothermic reactions, right? Those require energy, an input of energy. Okay, and so we call the transition from liquid to gas vaporization. We call the transition from solid to liquid. We do call it as melting, but we also call it fusion, right? Because we use here enthalpy of fusion and enthalpy of vaporization, okay? And so whenever we're going from solid to liquid or liquid to gas, they are endothermic. You should have positive values. Whenever you're going from a gas to a liquid, the process called condensation, or liquid to solid, the process called freezing, these are exothermic processes, right? They cause heat to be released. And so your value should be negative for these steps. Okay, and so my last kind of note about these is that you'll be given enthalpy of vaporization and fusion. but you might come across a problem like this, where you're going from a gas to a liquid, right? You're condensing, which again is gas to liquid, not liquid to gas. And so your enthalpy for this step here is actually the negative vaporization value they give you, right? So if they say the enthalpy change for vaporization of a compound is 10 kilojoules per mole, right, which again is from liquid to a gas, that means condensation would be negative 10 kilojoules per mole, right? Vaporization and condensation would be equal in magnitude but opposite in direction. And same with fusion and freezing, right? So if you're going from gas to liquid, remember to change the sign on your enthalpy change for vaporization. Sorry, one more was a note to myself. Okay, that concludes going over chapter 6 topics. Are there any questions? Okay, so here are the challenge problems. I'll probably keep each of them up for about 10 seconds before moving on. So if you need a picture for this one, just another couple seconds. Again, these will be posted tonight, and they'll also all be in the review video that I go over them as well. So you can pause them while going over that, try them yourself, and then kind of see what the solution to this is. And so I tonight made 7 problems, I believe. I believe 2 of them are gas, 5 are thermo problems. I just kind of had an abundance of thermo questions to ask about. Your exam is probably the normal length of a long answer exam, so you probably have just as good of idea as me at this point as to what that entails. It's probably about 4 or 5 questions. Some of them may have multiple parts. And again, it's long answer, so it's going to be pretty heavy calculation based. It'll probably be relatively split down the middle as to how the chapters are split up. Again, I just kind of made more thermo questions because, I don't know, a lot came to my head of ideas. And so this one's just a very classic enthalpy of formation questions. They will ask, not they will, like definitely, but they often will give a problem just like this on the exam. There's not really any curveballs, anything like that. They just want to see, do you know how to calculate the enthalpy change for a reaction given a table of values? But just like on the exam, something I tried to do is I tried to add some information you don't need to distract you and make sure you're paying attention. Okay, so this is something they will do on the exam if they give you a problem like this, is they'll throw in some distracting information. So for example, liquid water, also gaseous water. Okay, and so you have to make sure you use the right value because they are different. Okay, this problem is a phase change problem. It's actually very similar to one I made, I think, for Monday. It's still using benzene, which was similar to a problem. This one, you actually just go 2 different phase changes. So it's just a little bit longer, a little bit harder of a problem. But if you can do this phase change problem, and also number 7, it was a phase change problem, number 7 from last Wednesday. That's also a really good problem. If you can do both of those 2 with this one and that one with confidence, you should be relatively secure for phase change questions. And again, that was last Wednesday's session a week ago, and I think it was number 7. It was a heat exchange and a phase change problem in one, right? I think it was a piece of ice was added to tea. That was kind of the question. This problem is a pretty, again, a classic heat exchange problem, sorry, not a calorimeter problem. This time it actually asks at what temperature do these equilibrate, okay? And so you're gonna be looking for your final temperature in this one. I don't believe we've gone over an example like this, but this is a common type of question for them to ask, with the unknown being, what is the final temperature? And the algebraic process for this is just a little different from other types of heat exchange problems. And so I wanted to introduce this to you guys so that in case they ask it on the exam, it's not your first time seeing it. But again, this is asking for the final temperature, and just the way you have to approach this problem is a little bit more difficult and a little bit different from if they are missing a different variable. Okay, this one, again, it's pretty similar. This one's a calorimeter question, specifically a bomb calorimeter. And so if you're looking for kind of your typical calorimeter question, this is kind of one I would look to. I'm asking for the change in temperature here, which is not the most common thing to ask for, but is a very valid and fair question. And again, this is a relatively, I would say, straightforward kind of go-to textbook calorimeter question beyond asking for the change in temperature. That's slightly abnormal, but algebraically, it's pretty similar. And then the last challenge problem for tonight is, again, a question that they pretty much don't throw curveballs on. If they ask it pretty straightforwardly. And that's just a Hess's law problem, right? So using the information below, what is the enthalpy change for the above reaction? So this is going to be your goal reaction. These three down here are what I call your sub-reactions that you're going to have to manipulate, and also manipulate your delta H's as well. Okay. Okay. Are there any questions? At this point, I'm going to stop sharing. If there are any questions, I'm happy to answer them.